Hi kids, now we will be going with refraction. In the other class we have seen reflection at the plane surface and reflection at the curved surface. Before that we have started with loss of reflection. After that we have gone to reflection at the plane surface, then curved surface. We will go with the same pattern here. So before that you need to know some basic things. So one is refractive index denoted by mu. Refractive index of any medium is defined as speed of light in vacuum by speed of light in medium. So speed of light in vacuum is the largest. So speed of light in vacuum is denoted by c, which is almost 3 into 10 power 8 SI units, and in other medium it will be less than 3 into 10 power 8. So refractive index will be greater than 1, right? So and sometimes we may need a refractive index of air, water and glass. On average it is 1, on average it is 4 by 3, on average it is 3 by 2. Why I am saying average, you will understand it later, because refractive index depends on the wavelength. So for time being we will be going with average of that. Similar to what we have done in other class, we are going to learn loss of refraction. So incident ray, refracted ray and the normal at the point of incidence lie in the same plane. So basically when you send some ray from one medium to other medium, this medium I am calling it as incident ray medium, this medium I am calling it as refracted ray medium. So it won't be going in the straight line. We will see, we can derive it using Fermat's principle of least time taken, quickest path in the surroundings, but we are not going to derive it. You will be deriving that in kinematics anyway, so we will be taking it for granted. So yeah, so angle of incidence, angle of refraction. This is refractive index of incident ray medium, this is refractive index of refracted ray medium, so I am denoting it with mu y and mu r. So incident ray, refracted ray and the normal. Incident ray, refracted ray and the normal, they will be in the same plane. Now Snell's law says the ratio of sine of the angle of incidence to sine of angle of refraction of two media is constant. So sin I by sin r is constant, he said. So anyway, we won't be remembering this, we will be seeing it the other way. So Snell's law will be seeing it the other way. Mu y sin I equals to mu r sin r. So from here you can find sin I by sin r, which is mu r by mu I. Mu r is speed of light in vacuum by speed of light in that medium, speed of light in vacuum by speed of light in that medium. So which is constant. That's what Snell said, but we will be remembering this one. Mu sin theta is constant kind of. Mu 1 sin theta 1 equals to mu 2 sin theta 2. So you can take this simple question, you can pause and you can try it. If speed of light in vacuum is 3 into 10 power 8 meters per second, find the speed of light in water and glass. So mu value of water is given, mu value of glass is given. From there when you substitute mu is c by v, you will get the value as this much. Speed of light in water is this much, speed of light in glass is this much. Or you can understand, more the mu value, less will be the speed. Here you can see water speed is more, glass speed is less. Water speed is more, glass speed is less. And anyway you can see it here, glass mu is more, water mu is less. So more the mu value, less will be the speed. More the mu value, less will be the speed. Less speed we call it as denser medium, more speed we will call it as rarer medium. Less speed, denser medium, more speed, rarer medium. Right? So these are the terms which we will be using. Now we will see how the ray looks if it goes from rarer medium to denser medium. Rarer medium, speed will be more, so I am taking it as air, and this is water. Denser medium, speed will be less. Now mu sin theta is constant, so mu of air is less. Mu sin theta equals to mu sin theta. Now this mu is less, so this I will be more. This mu is more, this angle will be less. The other way of saying it is refracted angle will be less than incident angle. So if you are sending some ray, it will be bending towards the normal. So when a ray goes from rarer medium to denser medium, it will be bending towards the normal. We are going with Snell's law. Now you can see, if the water is not there, then it would have gone in this direction, but now it is going in this direction. You can see there is some angle which it has deviated. Now if this angle is I, this total angle is I, but this is r, so this will be I minus r. So deviation is going to be I minus r, which used to go like this, it has bent by I minus r. Now I am going by the opposite thing. Now I am sending the ray from denser to rarer. Again I can go with the same explanation, or if you see, I have copied the same figure with inverted arrows. The other way of saying it is, if you send the ray like this, it will go like this. If you send the ray like this, it will go like this. It can retrace the path backwards, right? Again, mu value is more, so I value will be less. Mu value is more, I value is less, mu value is less, so angle will be more. So here refracted angle will be more, you can see it here. When a ray go from denser medium to rarer medium, it will be bending away from the normal. It used to go like this, but now it is bending away from the normal. This angle is I, so this angle is I. Now this total angle is R, angle between normal and the refracted ray. This total angle is R. This is R and this is I, so this will be R minus I. So that's deviation. Deviation away from the normal, right? When you send a ray from rarer to denser, it will be bending towards the normal. When you send a ray from denser to rarer, it will be bending away from the normal. So that's the idea. But what will happen if I send the ray exactly like this? Angle of incidence will be 0, so sin I will be 0, so sin R also will be 0. So if you send the ray exactly like this, it will go undeviated. But if you send the ray like this, it is bending more than its actual angle, right? So when you keep increasing the angle, this will start bending even more. At certain point, you can see like this refracted ray will be grazing the surface. So yeah, so when I send the ray like this, it will go as it is. When I send the ray here, it will go somewhere like this. When I send the ray here, it will go somewhere like this. When I send the ray like this, it will be grazing. The refracted ray will be grazing. Now notice this careful. Till now, we were talking about only refracted ray, but understand one thing, there will always be reflection. So here this ray will be partially reflected and partially refracted. That reflection will be at the same angle. If this angle of incidence is I, angle of reflection will be I. Here also, this ray is partially refracted and partially reflected. This reflected ray will be at an angle I with the normal. Now here also, all the rays which you are sending here, they will be partially refracted and partially reflected. Now this ray, it will be partially reflected and partially grazing. Now if you send some ray which is more than this angle, which is going with more than this angle, then it can't go into the other surface, it will be coming back. The other way of saying it is, now there is no refraction possible, there will be only reflection, so we call it as totally reflected back internally. So total internal reflection we call it as total internal reflection. So basically this angle is important for us. For some particular angle, then then the refracted ray will be grazing. For some particular angle of incidence, the refracted ray will be grazing. That angle of incidence is called as critical angle. If you send the ray with more than critical angle, it will be totally internally reflected back. So that's the idea. Now how to find this critical angle? Again, I can apply Snell's law between this green color one and this white color one. Now understand, this will happen only when the ray is going from denser to rarer, because it has to bend away from the normal, right? So mu sin C equals to 1 sin 90, or if this has some refractive index, we would have taken mu sin 90. That's how we will be getting critical angle. So mu sin C equals to 1 sin 90. So that C is called as critical angle. So sin C is 1 by mu here, right? So that is called as total internal reflection. Now from here we will go with one very common question. It goes like, if there is a coin, but you can take it, size is like a point size. So if there is a coin in the water, and if you want to hide it, so what is the minimum radius of the disc you will be putting? Obviously, like if you cover the entire water, no one can see it, but we don't want to cover as much area, we need to cover as less area as possible. Now further, what you need to understand is, if some guy from outside is able to see this, he can see it only because the rays which are going from here, they will be reaching his eye. So if we can block the rays which are going to his eye, whoever is outside, then that's sufficient enough. Now we already know, if you send a ray like this, it will go as it is, so we need to block this one. If you send a ray like this, it will be bending away from the normal. If you send a ray like this, it will be grazing. So similarly, this is a 3-dimension thing. I have drawn only for this plane, right? So 3-dimension wise, you will be getting a cone kind of thing. So I need to block all those rays in this cone, because I don't have to block anything here, because whatever ray goes here, it will be total internally reflected back. Because you can see, angle of incidence is 0, it is increasing and became critical angle, it will become more than critical angle. So all these rays which are going here, they will be total internally reflected back. So basically I need to cover this area. Now to make the question easy, I have given the mu values 1 and 5 by 3. Understand, this total internal reflection thing will happen only when it goes from denser medium to rarer medium. So I need to find critical angle first. For that, 5 by 3 sin C equals to 1 sin 90, 5 by 3 sin C equals to 1 sin 90. From there I will be getting critical angle is 37 degrees. Once I know critical angle is 37 degrees, this height is given as 4. So if this is critical angle, I can take this triangle. This is also critical angle. So tan critical equals to R by 4, tan C equals to R by 4. tan 37 is 3 by 4, so r equals to 3, right? Okay, we'll go with some package questions. A light ray incident along the vector 2i cap, 4j cap and root 5 k cap strikes xz plane from medium 1 of refractive index 2 and enters into medium 2 of refractive index mu 2. The value of mu 2 for which the ray is just total internally reflected from the boundary. So we need to, so just total internally reflected. So the meaning is it will be hitting at critical angle. So we can take it is just grazing. We can take the angle of incidence is critical angle. So first of all we will understand x axis, y axis, z axis, I cross j is k. So ray is going along 2 I cap, 4 j cap and root 5 k cap. So ray is going like this, 2, 4, root 5. So this is the vector. So ray is going like this, and it is hitting xz plane. This is xz plane. So ray is going like this and it is hitting xz plane. Now you need to understand normal is going to be along y axis for this plane. So ray is hitting normal, you know. So basically you need to find angle between incident ray and the normal. Now how to find the angle between incident ray and normal? This is the incident ray. This is the normal direction. You need to find the angle between them. So I will go with dot product. A bar dot b bar is AB cos theta. Now dot product of these two is 4 into 1 is 4. Magnitude of A is root of this. Oh sorry, this has to be root 5. So that has to be root 5. Then you will be getting this magnitude is root of 2 square plus 4 square plus root 5 square. And B is 1 cos theta. So from here we will be getting cos theta is 37. So basically angle of incidence is 37. And angle of refraction is 90 degrees, right? So 2 sin 37. They have given this refractive index is 2. They are asking what is the other refractive index. 2 sin 37 equals to mu sin 90. So mu will be 1.2. Going to the next question. A slab of refractive index mu is placed in air and light is incident at maximum angle 60 degrees from the vertical. The minimum value of mu for which total internal reflection takes place at the vertical surface. So they are saying they are sending the rays with angle 0 to 60. I mean anything between 0 to 60. We need to make sure everything must be total internally reflected here. Now suppose, so basically what will happen if I increase this angle? If I increase this angle is going to increase. If this is 0, this will be 0. If I increase this angle is going to increase. If this angle increases, this angle decreases. So basically I need to make this total internally reflected. So for smallest angle of this thing, if I can make it total internally reflect, then all the other rays will be total internally reflected. Now for when will smallest angle happen here? When this is largest, this will be largest and this will be smallest, because these two are related, right? The more it is, the less it is. So even for the smallest angle possible, I need to make it total internally reflected. The meaning is this, even for the minimum value of this, it must be total internally reflected. If this is minimum, this will be maximum. If this is maximum, this is maximum. The other way of saying it is, if I can make this 60 degrees ray total internally reflect here, all the other rays in between will be total internally reflected. Now if this is 60 degrees, this has to be critical angle at least. If this is critical angle, this will be 90 minus critical angle from this right angle triangle. Then I can apply Snell's law here. Mu sin C equals to, it is just grazing 1 sin 90. Here 1 sin 60 equals to mu sin 90 minus C. So mu cos C is root 3 by 2. Mu sin C is 1. We need to find mu value. We are getting cos and sin. So we can square them and add them. You will be getting this much. So for 60 degree, for this, if refractive index of this material is this much, then for 60 degrees it will be just grazing. If it is 59 degrees, if this becomes less, this becomes less, and this will become more than critical angle, so it will be total internally reflected. So all the other rays will be total internally reflected. Going to the next question. An observer can see through the pinhole. The top of a thin rod of height h is placed as shown. The beaker's height is 3h and its radius is h. When the beaker is filled with the liquid up to height 2h, he can see the lower end of the rod. Refractive index of the liquid is. So basically they said this thing, height of the rod is h. Initially when he is seeing, he is observing the top of the rod. And this length is 2h given, radius is h, so this length is 2h. And this is totally 3h and this is h, so this is 2h. Now this is 2h and this is 2h, so I can say this angle is 45, this is 45, this will be 45. That's the information we need to gather from the initial thing. Now they are pouring water. When they start pouring water, now he can see only this ray. So basically the ray which is, or else we can send the ray in this direction. So he can see this ray. He can see this ray, but let us see what will happen if a ray is going in this direction. If a ray is going in this direction, it will hit here. But if you pour water, if a ray is going in this direction, it won't go in this direction anymore. It will be bending towards the normal and it will be reaching here. That's what they said. So if you send a ray like this, it will reach here. So if the ray is coming like this, it will reach his side. So that's the idea. So you are pouring water till certain point such that the bottom ray which is going, it will be reaching his side. Now we know this ray is making an angle 45 degrees with the horizontal. This ray is making an angle 45 degrees with the horizontal. So if this is normal, then angle of incidence will be 45. And they said this length is 2h, so this will be h. And this is given h. No, it's not given h. So from this triangle, this angle is 45, this angle is 45. So if this is h, you can calculate this to be h. Now this total length is 2h and this is h, so this will be h, right? Anyway, we'll see why we are doing that. So basically we need to find what is refractive index of the liquid. So we need to apply Snell's law. That's the only option we have to find the refractive index. So 1 sin 45 equals to mu sin r. So somehow if I can find sin r, then I can get the mu value. In order to find sin r, I will be going to take this triangle. From this triangle, this length is h, this length is 2h, this will be root 5h. So sin r is 1 by root 5. Sin r is 1 by root 5. You can substitute sin r is 1 by root 5, then you will be getting the required answer, right? A container contains water up to 20 centimeter and there is a point source at the center of the bottom of the container. The ceiling of the room is 1.5 meter above the water surface. Refractive index of water is 4 by 3. A ring of radius r floats on the water surface such that the center lies vertically above the source. If the radius of the ring is 15 centimeter, the radius of the shadow of the ring formed. So basically what does it mean by shadow? Missing of the rays. Now suppose remove the ring. If some ray is going like this, it will bend away from the normal and it will reach here. Now you are going to block that ray. So such rays, all such rays you are blocking, so you will be getting a shadow of shape ring. So if the ring was not there, this ray would have gone here, but you are blocking this ray, so here there will be shadow formed. You are blocking this ray also, there will be shadow formed. So it's 3 dimension, right? So you will be getting a ring, but bigger shadow, right? If the radius of the ring is 15 centimeter, radius of the shadow formed. This height is given 20 and this radius is given 15. So from there you can calculate this angle is 37. If this angle is 37, this will be 37. So angle of incidence is 37. So we need to find angle of refraction using Snell's law. Okay, I didn't write it here, but you can calculate using Snell's law. 4 by 3. 4 by 3 sin 37 equals to 1 sin theta. So from here you will be getting angle of refraction as 53. Now once you get that, this length is given as 1.5. Again you can take this triangle and you can calculate tan 53. From there you will be getting this length as 2. So if this length is 2 and this is 2 meters, this is 15 centimeters. So this radius is 2 meters plus 15 centimeters, which is 2.15 meters. So option A is correct. Okay, I have directly marked option D is wrong because they were saying all the light rays coming out of the source will retract out of the liquid. Now this is denser medium, this is rarer medium. So the rays which are going with more than critical angle, they will obviously total internally reflect. Now the second option, the minimum radius of the ring for which the shadow cannot be formed. The minimum radius of the ring for which the shadow cannot be formed. So basically, if some ray is total internally getting reflected here, if you place a ring there, shadow won't be formed. So if you can block the rays which are going outside, only then shadow will be formed. So if you are keeping a ring where the rays are not going outside, shadow won't be formed. So we will see where that will happen. So this is the last ray which you can block, which is going and hitting at an angle, critical angle, right? So if this is critical angle, this will be critical angle. How to calculate critical angle? Mu sin critical angle equals to 1 sin 90. So from there sin C is 3 by 4. So I am drawing the triangle, so that sin C, I can calculate any angle, any sin theta or cos theta, sin C or cos C or tan C. Now I need R. So from there I will be getting tan C. Tan C equals to R by 20. Now tan C here is 3 by root 7. From there I will be getting R is 60 by root 7. So if the radius of the ring is anything between 0 to 60 by root 7, we will be getting a shadow. If the radius of the ring is more than 60 by root 7, this ray anyway will be total internally reflected back, so there won't be any shadow getting formed. Going to the next option, keeping the radius 15 centimeter. If the level of the water is varied, liquid is varied, the height of the liquid level at which the shard of the ring disappears. Again going with the same logic, that's the last ray, right? Last ray which is going to hit critical angle. This is critical angle, this is critical angle, but now they have fixed this, they are asking you to find this. Again you will be finding sin C and you will be drawing the triangle, and then again you will be using tan C, then you will be getting height. So this is almost same as option B, but there they have given H and they asked you to find R. Here they are giving R and they are asking you to find H, right? Okay, so going to the next part, suppose this is a glass slab and if you send a ray from air to glass, then what will happen? Ray will be bending towards the normal. If the angle of incidence is I, then the angle of refraction will be R. I can apply Snell's law, 1 sin equals to mu sin R. This entire thing is glass only. Now this ray will be coming and hitting here. Now you need to understand these two angles will be same. Why they are same? Because these two are parallel to each other. These two surfaces are parallel to each other. If the surface was not parallel, then this won't be R. Now that's the idea. So if the surfaces are parallel to each other, then this R and this R will be same. Now if I apply Snell's law, mu sin R equals to 1 sin I dash, let me say I dash, but I can see these two look same. So I equals to I dash. So whatever will be this angle, it will be the same angle. Now I can keep many slabs and I can say mu sin theta, mu 1 sin theta 1 equals to mu 2 sin theta 2 equals to mu 3 sin theta 3, mu 4 sin theta 4 and so on. So mu sin theta is constant when the slabs are parallel, I mean when the surfaces are parallel to each other, right? So we'll extend that argument with this, I mean we'll use that argument in this particular question, which will be much easy. We have understood when the slabs are parallel to each other, mu sin theta is constant. A ray of light is incident on glass slab at a grazing incidence. Refractive index is varying with y. The refractive index of the material of the slab is given, thickness of the slab is given, thickness of the slab is given. So they are asking what will happen to the ray. Now this refraction phenomena can be explained basically by Huygens law only. We need to understand the wave nature. Now when a ray is going like this, you don't have any argument like why it will be bending the upward direction when you go with ray nature, because the slab is like this and the ray is going at 90 degrees, it has to go at 90 degrees. But when you understand the wave nature, when you talk about beam of light rays, or when you talk about the wavefront, okay, so these things will be the upper things will be having less speed. So this will travel less speed, this will travel the points on the wavefront, right? This will travel less distance, this will travel more distance. Now when I draw the new wavefront is going to look like a curved one. So the new ray will be perpendicular to that curved surface, right? So you can explain this phenomena or refraction phenomena only using Huygens principle. Anyway, let us not bother about that. So it will be taking some curved path. So let me say at any position if I take a slab, then this is the normal. So this is the angle and this is the angle. So mu sin theta, we have already understood there are many slabs here. So no matter how many slabs are there, what we can do, mu sin theta is constant. So here mu is 1, angle is almost 90 degrees, right? So 1 sin 90. So we are applying Snell's law between this point and this point, because we know if there are many slabs, then you can use mu sin theta is constant. So 1 sin 90 equals to mu sin theta. Now mu theta, so we need to do something to get the curve equation. For that we will be writing the slope here. If this angle is theta, if I draw the tangent, then this angle will be theta, this will be 90 minus theta. So slope of this curve, that is dy by dx, will be given by tan of 90 minus theta, which is cot theta. So from here I can see, I can do something. So cot theta, from here I can find sin theta and I can find cot theta. Sin theta is 1 by mu. So from there I will be getting root of mu square, mu is given 1 plus root of 1 plus y. So from here you will be getting this thing as this. Dy by dx is cot theta is adjacent by opposite. So now there are two variables, you can bring one variable to one side, other variable to other side, and when x is 0, y is 0 given in the question. So at any x, y value will be y. This is the curve equation. So which will say option C is correct. Option C is correct. Now in the last option we can substitute y equals to 2. When you substitute y equals to 2, you will get x equals to 2 root 2. Option D is also correct. The ray will become more and more parallel to face AB? No. This is face AB. Already it is parallel. How it will become more and more parallel? It is like bending. Oh, I don't see what is option A. The ray will undergo continuous refractions or reflections. Refractions will obviously happen, and yeah, you can take like many slabs. So whenever refraction will be happening, there will be partial reflection also. So you can consider there will be reflection also partially. Now going to the next part. If there is an object here, if I talk about the ray which is going in this direction, it will go undeviated. This is air and this is water. An object is in air and the rays are coming from that object into water. This ray will go undeviated. This ray will be bending towards the normal. Now I have drawn this ray at bigger angle, but we are talking about only smaller angles. The other way of saying it is, I am talking about the rays which are going in only in these surroundings, As the figure is going to become clumsy, I am drawing it little away. So we are talking about the rays which are going only in the surroundings of the normal, right? So the meaning is this angle is small. Now if a guy is observing from here, he will be seeing this ray coming from somewhere and he will be seeing this ray. So basically if a guy is observing from water, if a person sees from water, he will be feeling these rays. These two rays are coming from somewhere here. The other way of saying it is, if the object is here, the guy who is observing from the water, he will be feeling the image is here. Or if you are inside water and if you are seeing a bird, you will see the bird is at somewhere this height. So that's the idea. If the actual height is h, we need to find what is that apparent height the bird is at. So we'll go with Snell's law. So if this is angle of incidence, so this is also I. This is angle of refraction, so this is also R. Now we can see two triangles here. From these two triangles we will find the common length is this thing. So we will find this common length in those two triangles and we will equate them. So if I take this triangle and if I use tan theta, I will be getting that length as h tan I. This length is going to be h tan I. If I take this triangle, I will get this length as h tan I. If I take this big triangle, I will get this length as x tan R. That is x we need to find, right? So this will be x tan R. So h tan I equals x tan R. From there I will be getting x equals to h tan I by tan R. But for small angles, tan theta will be almost same as sin theta. So I will be writing sin tan I by tan R as sin I by sin R. Now what is sin I by sin R? 1 sin I equals to mu sin R, Snell's law, right? So what is sin I by sin R? It is mu. So mu into h. That must make sense because we understood it is more than h. It is more than h and we are multiplying h with more than 1, right? Mu value will be more than 1. Now going by the other thing, if the object is in water and if we are observing from air, or if there is a fish or coin inside the water and if you are observing from air, you will be feeling it is little upwards. That's also we can see. This guy, he will be seeing this ray and he will be seeing this ray. This ray will go undeviated, this ray will be refracted, bending away from the normal. So the guy who is observing from here, he will be feeling those rays are coming from here. But actually they are coming from here, but this guy will be feeling they are coming from here. So this is the actual object, but we will be feeling that is here. So that's the image formed because of the refraction, right? So if there is a coin here, we will be feeling that is somewhere here. Now if this is the actual depth d, this is the apparent depth, we need to find what is the apparent depth. Again, this angle is I, so this angle is I, this angle is R, so this angle is R. Again we will take this triangle, we will find this common length, we will take this triangle, we will find that common length and we will be equating them. Before that we can apply Snell's law. This is denser, this is rarer, so I am taking this as 1 and this is mu. So mu sin I equals to 1 sin R. So that I have written. Now by taking this triangle, I am finding the length. That length is going to be y tan R. Now if I take this big triangle and if I find this length, then it is going to be d tan I. Then when I equate, again I am going with small angle approximation. For small angles, tan I is almost sin I and tan R is almost sin R. So y will be d sin I by sin R. What is sin I by sin R from here? It is 1 by mu. That makes sense because we know its value has to be less than d. So we are dividing with greater than 1. So this thing I will be using very frequently. So if you are seeing a bird which is in air and when you are observing from water, you will be feeling that height is more than the actual height. As it is more, we will multiply with mu. When you are observing fish from air, then you will be feeling that it has lifted up. So as this distance is less, I will be dividing with mu to find that. So this I will be using very frequently. So it's better to remember that. Okay. So we'll go with some questions. A small air bubble is inside a glass cube of side 32 centimeter. When viewed from one face, the bubble appears to be at 15 centimeters, and viewed from opposite face, it appears to be at 5 centimeter. The refractive index of the cube. Basically, there is a bubble here. When you are observing from this side, you are feeling, obviously, like you are observing from air, so you will be feeling like it has shifted closer to you. So you are feeling it is somewhere here, and this distance is 15 given. And when you are observing from here, you are feeling it is somewhere here, which is 5 centimeter given, and the total length is 32 given. So let me say this distance is d1 and this distance is d2. So if the object is at a distance d1, then image is 15. So I can say image has to be at d1 by mu, right? We have just seen when it is shifting upwards, we will divide because it is less, right? So this distance I can call it as d1 by mu. d1 by mu is 15. d1 by mu is 15. d2 by mu is 5. d1 by mu is 15, d2 by mu is 5, but we know d1 plus d2 is 32. So d1 is 15 mu, d2 is 5 mu, so 20 mu, 15 mu plus 5 mu is d1 plus d2, which is 32. So from there we will be getting mu value as 1.6. A bird in air is diving vertically downward over a tank with speed 5, while the base of the tank is silvered. A fish in the tank is rising upwards along the same line with speed 2, water level is falling at a rate 2. Refractive index of water is given. Speed of image of fish as, okay, we'll go with option by option. So we'll go with first option. Speed of image of fish as seen by the bird directly. So now you need to understand one thing. The rays which are coming from fish, they will directly refract and they will be reaching the bird's eye. Now there are some rays which are going this way, they will be reflected here, again they will be refracted here, again reaching the bird's eye. So bird will be seeing two images of the fish. They are talking about direct refraction image first. In the option here, they are talking about the image formed because of the refraction here. Speed of image of fish as seen by the bird directly. Now this height is h and this distance is d, and they said bird is going down with 5, water level is falling and fish is going upwards. Now I am calling this as h and this as d. Now if this distance is d, if some guy is observing from here, then he will be feeling the image is somewhere here where this distance is d by mu. Then the distance between them will be h plus d by mu. They are asking at what rate the length is varying. So that is differentiation of this entire thing. Differentiation of this entire thing is differentiation of this plus differentiation of this. Now h is varying at a rate. At what rate it is varying? This is going down with 5, this is going down with 2. So this total thing is reducing with 3. So h dash is minus 3. Now what about this? This is reducing at a rate minus 2, minus 4. It is reducing at a rate 4. So minus 4. And refractive index is given. So when you do the calculation, it will turn out to be minus 6. The other way of saying it is the distance between bird and the image of the fish observed is reducing at a rate 6. So option A is correct. Now going to the second option, speed of image of bird as seen by the fish. Now fish is seeing the bird image. This length is h, but it will be feeling it is those rays are coming from here, so which is mu into h. So image will be mu into h and total distance is mu into h plus d. Bird is here, but this guy will be feeling image is here where the distance is mu into h. So the distance between them is d plus mu into h. They are asking at what rate it is varying. So the differentiation of this is differentiation of this plus this. H is varying at a rate minus 3. D is varying at a rate minus 4. When you substitute the values, you will be getting minus 8, which says option B is correct. Now going to the next part, speed of image of fish as seen by the bird after reflection from the mirror. So I am calling this as capital D now. Now the rays are going like this and hitting the mirror. Now because of this, image will be formed somewhere here where if this distance is d, image will be formed at d, capital D. So image is formed here. Now these rays, whatever rays are going here and getting refracted, now those rays when you extend them, they will be meeting here. So basically what is the object distance? Object distance is d plus d plus d. small d plus capital D plus capital D, right? So if those rays are getting refracted, we will be feeling the image has shifted upwards, the image has shifted upwards, right? So what is the distance of that object? Distance of that object is d plus capital D plus capital D. So its image will be formed shifted little upwards. How much upwards? The total distance by mu, right? Total distance is capital D plus small d by mu. So now new image will be at this distance, which is 2 capital D plus small d by mu. So image is here. Now apart from that, this distance images will be measured from here, right? So what about this distance? This is h. So the distance between bird and the image of the fish is h plus this thing. Now they are asking at what rate it is varying. So the differentiation of this is this plus this, right? Now this d dash, this is varying, this is increasing at a rate 2 and small d is decreasing at a rate 4 and h is decreasing at a rate 3. When you substitute the values, you will be getting the answer as -3, which says option C is correct. So what we have done, we have taken the reflection here first, so image will be formed here. Now that will act as object for this guy, so that will be shifting, the image will be shifting upwards. So we will be taking total distance by mu. Now apart from that, there is h here, right? Now similarly we will go here for the fourth option, speed of the bird as seen by the fish after reflection from the mirror. So bird is here. Now the rays which are entering the water, so we will be feeling like they are coming from here, So after refraction, we will be feeling those rays are coming from here, which is mu into h. Now this will act as object, for this mirror. So that is capital D plus small d plus mu h is the distance. Capital D plus small d plus mu h is the object distance. So image will be formed at capital D plus small d plus mu h. Now those rays will be reflected. So the reflected rays will be feeling like they are coming from capital D plus small d plus mu h distance. So fish will be seeing that they are coming from that distance, right? So what is the distance between the fish and the image? Now this distance is capital D plus small d plus mu into h. Apart from that, there is d here. So this is the image distance and this is the distance between the fish and the mirror. So they are asking at what rate it is varying. So differentiation of this plus differentiation of this. H is varying at a rate, reducing at a rate 3, D is reducing at a rate 4, capital D is increasing at a rate 2. When you substitute the values, you will be getting 4. So option D is wrong according to me. Now going to the next question. You can remember the result after doing the question. A point object O is placed in front of transparent slab at a distance x from its closer surface. So this is the transparent slab, and from this closer surface, object is at a distance x. This is x. It is seen from the other side of the slab by light incident nearly normal to the slab. So the angles are small. So we can go with whatever we have derived, mu into h or t by mu. The thickness of the slab is t and refractive index is mu. Show that the apparent shift in the position of the object is independent of x. So they are saying the shift is going to be not depending on the x value and find its value. So basically they are asking you to prove shift due to the slab is that much, and you need to remember that result. So we will see the formal derivation. Object is here. When the ray is going like this, after refraction it will be bending towards the normal. So if a guy is observing from here, he will be feeling that ray is coming from somewhere here. Now that ray will go and it will be bending away from the normal. Now you need to understand this ray and this ray will be parallel. These two rays will be parallel because we have already seen they are like, it's a slab, right? So this angle and this angle will be same. Angle of incidence will be same. So there is refraction happening here. So one image is getting formed here. Now that will act as object for this refraction, and image is getting formed here. So we need to see what is this distance, what is the shift, right? So if this, they have given this distance is x, they have given this distance is x. Now you know when the object is in air and when you are observing from water, you will be feeling the image is more than the actual distance. So as this is x, you will be feeling that image distance is mu into x. Object distance is x, so image distance is mu into x. Now that will act as object for this refracting surface, now which is at a distance mu into x plus t. Now when you are observing something, some ray coming from water or denser medium, and when you are observing from rarer medium, you will be feeling the distance will be shrinking by how much? Actual distance by mu. It will become actual distance by mu. What is the actual distance? T plus mu x. T plus mu x. So this distance is going to become T plus mu x by mu. T plus mu x by mu, which is x plus T by mu. X plus T by mu. So x plus T by mu from here. From here. So what was the actual distance from here? T plus x. Actual distance is T plus x, but final image distance is x plus T by mu. So what is the shift? This is the shift. Shift will be this total distance minus this total distance, that is T plus x minus x plus T by mu. T plus x minus x plus T by mu. You can see x and x will get cancelled, so you will be in T into 1 minus 1 by mu. So when you are observing from this side, you will be feeling the image is somewhere here. So what is the shift you will be feeling? You will be feeling that shift is T into 1 minus 1 by mu. Now when the rays are diverging, when the rays are going diverging, you will be feeling the shift is towards the slab. Now suppose if the rays are going this way, so basically if the slab is not there, they would have met here. So if the rays are going this way, if the slab is not there, they would have met here. Because of the slab, what will happen? It will go like this, and it will meet here. So when the rays are converging, shift will be T into 1 minus 1 by mu away from the slab. When the rays are diverging, shift is towards the slab. When the rays are converging, shift will be away from the slab. Magnitude wise, it is T into 1 minus 1 by mu, right? And yeah, you should be remembering that result. We'll be using it very frequently. Shift due to slab is that much, which doesn't depend on the position. That's one more important thing, which doesn't depend on the position where you are placing it. So the easy example where you can understand it is this. An object is placed 21 cm in front of concave mirror and radius of curvature 20. A glass slab of thickness 3 cm and refractive index 1.5 is placed close to the mirror in the space between the object and the mirror. Find the position of final image formed. Now the actual object is here, but after refraction through the slab, we will be feeling the rays whichever are coming, they are coming from somewhere here where the shift is T into 1 minus 1 by mu. T into 1 minus 1 by mu. T value is given, mu value is given. When you substitute, it will turn out to be 1 cm. So this mirror, he will be feeling the rays are coming from 20 cm rather than 21 cm. This mirror will be feeling the rays are coming from 20 cm. The other way of saying it is 20 cm is nothing but center, right? Radius of curvature is 20. So this guy will be feeling these rays were coming from center. So they will be hitting normally. I mean, they will be hitting like angle of incidence will be 0, right? So if they are hitting like this, they will be reflected back as it is. Now this ray, it went like this, it went like this. Now if you are sending some ray like this, it will go like this, it will go like this, and the image will be formed exactly at the same point where the object is, right? So rays will be retracing the path. So we will use this logic lot many times. If the image is formed at the same point, we will say like the rays are going to hit the mirror perpendicularly and it is going to retrace the path. Okay, you can look into the next question. In the given figure, find the distance between two images seen by the observer. So observer is here, the rays will go like this. So after refraction through the slab, he will be seeing some rays, and some of the rays will be going and hitting the mirror. Those rays will come to him, so he will be seeing the other image. So he will be seeing two images. One is just because of refraction, one is because of refraction and reflection. So shift will be T into 1 minus 1 by mu. T value is given, mu value is given. When you substitute, you will be getting it as 5 cm. The meaning is, if the rays are coming from here, he will be feeling those rays are coming from here. That is first image, right? Which is 5 cm from here. Shift will be towards the slab. So yes, so he will be feeling one image is here, which is 5 cm from the actual point. Now anyway, now even the mirror guy also will feel like those rays are coming from here, right? Those rays are coming from here. When you have taken the slab effect, you are seeing like the image will be here. So basically you can remove the slab now and you can take the object is here, right? The other way of saying it is, if the rays are going this way, this guy and this guy will be feeling the rays are coming from here. So now this will act as object for the mirror. Now what is that object distance? This is 5 and this is 45. So object distance is 40. And the incident ray is going in this direction. So that is positive direction and this is negative direction. And radius of curvature, center is that side. So radius is positive and focal length is also positive. So when you use U is minus 40, object distance is minus 40, negative side, and focal length is plus 10, you will be getting V is plus 8. The meaning is image is formed on that side. image is formed on that side, positive side. The other way of saying it is virtual image. So virtual image, and the rays will be reflected, and this guy will be feeling that image is somewhere here. Now they are asking what is the distance between those two images, right? So from here to here, from pole to here it is 40, from here to here it is 8, so it is 40 plus 8, 48, right? Now you can do this question again by yourself. We have already done this question. Now you can take shift, this shift and this shift, right? And this shift plus this shift must be equals to 32 minus 20. Anyway, that's up to you. Okay, now we will be going with prism. As we already know, angle of incidence, normal and refracted ray will be in the same plane. So we are just taking that planar figure of prism. So first of all, I will be defining something. I will tell you what is happening here. This angle is called as angle of prism. This angle is called as angle of, this is the incident ray. After refraction it will be going something like this, and after refraction here it will be going something like this. So it will be bending towards the normal, it will be bending away from the normal. Incident ray, it will be bending towards the normal. Incident ray, it is bending away from the normal. So angle of incidence is called as I1. Now it is going like this. So this is the normal, right? Angle of incidence, normal, incident ray, normal, so angle of incidence. Normal and refracted ray, so angle of refraction. This is the ray hitting and this is the normal, so this is the angle here, so I am calling it as R2. So I will call this as angle of refraction only, because I see this is I1 and this is I2, and I will call this R1 and R2. Inside the prism I will call it as R1 and R2, outside the prism I will call it as I1 and I2 for easy understanding. Right, now you can see it used to go like this, but it bent like this. Now this angle is I, so this angle is I, this is R1, this is I1, so this is I1, this is R1, so this will be I1 minus R1. This is I1, angle between these two lines, that is, this is I1, this is R1, so this will be I1 minus R1. Now it used to go like this, but it is bending like this. So this angle is I2, so this angle is I2, this is R2, so this will be I2 minus R2. So you can see here it has deviated by I1 minus, it used to go like this, but it has bent by I1 minus R1 in clockwise. Now again it used to go like this, again it has bent in clockwise I2 minus R2. So what is the total bending or what is the total deviation? This plus this. So I1 minus R1, it used to go like this, but it has bent by this much angle, right? It has bent by this much angle, which is I2 minus R2. It has bent by I1 minus R1 here, it has bent by I2 minus R2 here. So what is the total deviation? I1 minus R1 plus I2 minus R2. So total deviation will be given by I1 plus I2 minus R1 plus R2. Now apart from that, I can see this triangle, this is the normal, this is R1. So if this is R1, this total angle is going to be 90 minus R1, this total angle is going to be 90 minus R2. So when I take this triangle, A plus 90 minus R1 plus 90 minus R2 will be 180. 90, 90, 180 will get cancelled. I will be getting R1 plus R2 is A. R1 plus R2 is A. So this plus this is A. Anyway, you people will be knowing it is like exterior angles, summation, something like that, right? So that's the first thing. This is the second thing I have written. Now apart from that, I can use Snell's law here. 1 sin I1 equals to mu sin R1. Mu sin R2 equals to 1 sin I2. So this is sum of the angles of the triangle is 180. This is the deviation, that is bending of the ray, and Snell's law here and Snell's law here. So those things, if you know those things, then you can do anything from prism. Now deviation. If we talk about deviation specifically, we got deviation is I1 plus I2 minus R1 plus R2. And we got R1 plus R2 is nothing but A. R1 plus R2 is nothing but A. So deviation, sometimes you will write as I1 plus I2 minus A. So that's up to you. Now for minimum deviation to happen, actually you can prove it mathematically, but you can take it for granted or symmetrically. For minimum deviation to happen, these two angles must be same. These two angles must be same. If these two angles are same, that is, if these two angles are same, then you can easily prove yourself, convince yourself, these two angles will be same. So if these two angles are same, these two angles will be same. That's the time where it will be minimum deviation. So for the minimum deviation, I1 equals to I2, so let me call it as I. So R1 will be equals to R2, let me call it as R. And we know R1 plus R2 is A, so R is going to be A by 2. A by 2. So at minimum deviation case, this is going to be 2i minus 2r, right? So minimum deviation will happen when I1 equals to I2, R1 equals to R2. I am not giving much formula here, so these are the basics. You can solve any question from these basics. Now we will see how to solve it. A light ray is incident on face AB of prism ABC as shown in the figure. The second prism is kept in such a manner that emergent ray from prism ABC is falling normal on face A dash B dash of the prism A dash B dash C dash. The net deviation produced by the optical system of the two prisms in degrees. So basically it is going like this. Angle of incidence is given, refractive index is given. So you can find what is the angle of refraction by using Snell's law. 1 sin 53 equals to mu sin theta. Mu sin R1, this is R1, right? So from here you will be getting R1 is 37. So R1 will be 37, and we know R1 plus R2 is A, 74, right? This plus this must be equals to 74. There is something wrong written here. This is 74 minus 37 is 37. So R2 will be 37. This will be 37. So we applied Snell's law and we got this angle is 37. By using triangle properties, we got this angle is 37. Now we know if this is 37, this is 53. So if this is 37, this will be 53, or by using Snell's law. Now it is going and hitting here perpendicularly, so it will go undeviated. As this is 90, this is 37, this will be 53, this will be 37. Again, if this is 37, by using Snell's law, you will get this as 53. Now it used to go like this, but it has bent how much? 53 minus 37. It used to go like this, but it has bent how much? 53 minus 37. It used to go like this, but it has bent again how much? 53 minus 37. That is 16. It has bent 16 here, 16 here, 16 here. What about the direction? It has bent clockwise. It has bent clockwise. It has bent clockwise. So 16, 16, 16 all are clockwise. So you will be getting total deviation of 48 degrees, right? So this is 74 minus 37 is 37. This one is wrong, written wrong here. Next question. An isosceles prism of angle 45 degrees is found that when the angle of incidence is same as prism angle, the emergent ray grazes the surface. So you need to find what is the refractive index of the material. So they said angle of the prism is 45. I didn't draw the figure. Probably you can draw the figure to understand it better. Prism angle is 45, they said, and incident angle is 45, they said, and on the other side it is just grazing, they said. So there it is critical angle. So R2 is critical angle. R2 is critical angle. And we know R1 plus R2 is A, and A is given 45 degrees. So R1 will be A minus R2, which is 45 minus critical angle. 45 minus critical angle. Now anyway, so why we are doing this? We need to figure out what is mu value. So if you want to figure out what is mu value, we need to apply Snell's law. So we are applying Snell's law at the second point, that is mu sin C equals to 1 sin 90. From there I will be getting, so what I need to find? I need to find mu value for that sin C. Okay, so I am drawing the triangle so that if I need it, I can use it. Okay, so basically I applied Snell's law at the second point, I applied Snell's law at the first point. At the first point it is 1 sin incident angle equals to mu sin refracted angle. At the second point, mu sin refracted angle equals to 1 sin that other angle, I2, right? So I applied Snell's law at both the points. From here I will be getting relation between mu and sin. Now if I want to find mu value, I need to figure out what is sin R1. So if I want to figure out what is sin R1, I will be taking it here. Now from here I need to find sin R1, so I will take sin of this. Sin of R1 equals to sin 45 minus C, that is sin A minus B. Sin A cos B minus cos A sin B. Now what is sin C and cos C from this triangle? You can substitute it back. From here mu sin R1. Mu sin R1 is root of mu square minus 1 by root 2 minus 1 by root 2. So mu sin R1 I just substituted from here. Mu sin R1 I just substituted from there. Root 2, root 2, root 2 will get cancelled. From there we will be getting 1 plus 1, 2, and I have taken square. So mu square is 5. So what all things we have done? We have used Snell's law at both the points, and we understood second angle is critical angle, and these values were given in the question, and we know this information from the triangle property, and we are just using some math, right? A prism of refractive index root 2 and apex angle A as shown. Light is incident from PQ side at an angle I. This is angle of incidence, and refractive index is mu. Okay, so the options, there is option A here. Okay, I'll read it out. if A equals to 40, option A says if A equals to 40, then light incident at all angles will emerge from the surface PR. Now, in all the options they are talking about whether total internal reflection will happen or all the rays will be refracted. So, basically this is I1, okay, I need to see R2. Now, R2 minimum value. R2 value varies from certain region to certain region. So, if R2 minimum value is critical angle or fine. So, if R2 can be critical angle, if R2 is critical angle or more than critical angle, it won't be going on to the other side, right. So, for R2's minimum value, if it is total internally reflecting, then for any value of R2, it will be total internally reflecting. This is the idea. For R2 to be minimum, we know R1 plus R2 is constant, that is this angle. So, if R2 is minimum, then R1 will be maximum. If R1 is maximum, then I1 will be maximum. R2 minimum, we need R2 minimum and we need to see that guy is total internally reflected or not. We need R2 minimum. So, if we want to find something about R2 minimum, we need to find something about R1 maximum. R1 maximum, if we want to find, then we need to understand something about I1 maximum. But we know I1 maximum is 90. So, if I1 maximum is 90, by using Snell's law, you can understand this will be critical angle. So, R1 maximum value is critical angle, which in this question is 45. For R2 to be minimum, R1 has to be maximum. For R1 to be maximum, I1 has to be maximum. I1 maximum is 90. So, R1 maximum is critical angle. So, yeah, so that's the idea. R1 maximum is critical angle. So, yeah, so R1 maximum plus R2 minimum is A. R1 maximum is critical angle. So, in the first question, in the first option, they are saying A is 40. So, when I substitute 40, this is R2 minimum. I am not writing minimum every time. It is R2. The meaning is R2 minimum. So, R2 minimum is minus 5. Minus 5. So, minus 5 in the sense, according to our figure, this is the angle. So, it will be going the other side. So, normal will be coming on the other side. So, angle will be turning out to be 5 only. So, R2 minimum, magnitude wise it is less than critical angle. So, it will be passing on to the other side. We do not have any problem. So, all the rays will be emerging to the other side. We do not have any problem. Look at the second option. If A is 80, then R2 will turn out to be 35. R2 minimum. Minimum value of R2 is 35, which is less than critical angle. So, all the rays will be emerging. We will talk about option A little more. So, we are talking about, so for minimum value of R2, for minimum value of R2, it is going out. So, when R2 is increasing, we need to see what is the maximum value of R. Now, what is the maximum value of R? If I want to find maximum value of R, then it has to be minimum value of R1. Maximum value of R2 implies minimum value of R1. Minimum value of R1 is 0. So, basically when you send the ray normally, we need to see. So, when you send the ray normally, what will happen? This angle will be 90. So, this will be 90 minus, yeah, this angle is given as 40, right. So, this angle is 40. So, this angle is going to be 50. So, this angle is going to be 40. So, angle of incidence is going to be, I mean R2 is going to be, yeah, R1 plus R2 is A, right. R1 plus R2 is A. R1 plus R2 is A. So, for R2 maximum, R1 has to be minimum, which is 0. So, basically R2 maximum is going to be A. So, if it is 40 degrees, still it will be going out. So, whether R2 is minimum or maximum, we understood the rays will be going out. So, basically in option A, all the rays will be coming out. What about option B? Option B, we found out R2 minimum value. R2 minimum value is 35. So, for minimum value of R2, it will go out. What will happen for maximum value of R2? So, that is when you send it like this. Angle of R2 is going to be A value, right. R2 is going to be 80, which is more than critical angle. So, it is not going to go out. It will be total internally reflected back. It will be total internally reflected back. So, only some rays will be going outside, some rays will be total internally reflected back. What about option C? Again, in option C, when you substitute, you will be getting R2 is 55. So, minimum value of R is it's getting total internally reflected. So, if minimum value of R is total internally getting reflected, then any value of R will be total internally reflected. TIR will happen. So, all the rays, in the third case, all the rays will be total internally reflected. Now, option D is kind of formula, some people will remember it, I don't know. Whatever is the value of A, light will emerge from the surface PR. Whatever is the value of A, light will emerge from the surface of PR for some value of I. We have seen in option C, it won't happen. In option C, all the rays are total internally getting reflected. So, from here itself, we can say option D is wrong, or we can prove it like little better. For what angle it will be all the rays will be total internally reflected back. So for R2 minimum, if R2 minimum is greater than critical angle, then all the rays which are hitting there, they will be total internally reflected back. If for minimum value, if it is total internally reflecting back, then for any value, it will be reflecting back. So yes, so for this to be minimum, this has to be maximum. This maximum is C, right? So R1 plus R2 is A, I mean minimum. For R2 minimum, R1 has to be maximum, maximum value is C, we already understood. So R2 is A minus C. So if R2 is more than critical angle, that is if A minus C is more than critical angle, then all the rays will be total internally reflected back. If R2 minimum is more than critical angle, then all the angles will be more than critical angle, all the rays will be total internally reflected back. So basically if A is greater than or equals to 2C, equal to we don't talk much about it, it's grazing thing. So if A is greater than 2C, then it will be all the rays will be total internally reflecting back. So in option C, 100 is more than 2C, 100 is more than 2C. So all the rays are total internally reflecting back, right? I think people spend little time over here and understand what it is. Then going to the next part. So what will happen if angle of the prism is small? I am doing the same thing. It's the same previous slide. This one, this is from sum of the angles of the triangle. This is the deviation. This is Snell's law. This is Snell's law. If A is smaller, if A is very, very small, where I can go with the approximation of sin theta is almost same as tan theta, which is same as theta. If this is small, then R1 plus R2 is A, we know. So if A is small, R1 has to be small, R2 has to be small. If R1 is small and R2 is small, then I1 is small and I2 is small. So if they are small, what I can do, I can apply Snell's law like sin I1 is almost same as I1, sin R1 is same as R1. This is R2 and I2 almost. Those are in radians. Now deviation is going to be I1 plus I2 minus R1 plus R2, which we have already derived for general case only. But I1 is going to be mu R1, I2 is going to be mu R2. Okay, so you can substitute it in radians, or if they ask in degrees, you can directly substitute in degrees, right? Because here we are getting only one angle. So if deviation they ask in radians, you can substitute A in radians. If deviation they ask in degrees, you can substitute this in degrees. Now you need to understand, this deviation is same for all the angle of incidence. It doesn't depend on the angle of incidence, mu minus 1 into A, unlike big angle prism. So for small angle prism, deviation for any ray is going to be almost mu minus 1 into A. For any ray it is going to be mu minus 1 into A for small angled prisms. Now you can see this is small angled prism. A thin prism of refractive index 1.525 is combined with another thin prism of refractive index 1.7 angle 3. And I will talk about dispersion later. So anyway, we will see it is going without deviation. Deviation due to one prism will be mu minus 1 into A, as it is small angled prism. Due to the other one also mu minus 1 into A. The summation has to be 0, they are saying. So deviation due to the first one plus deviation due to the second one is 0. These values were given and they are asking this value, giving this value, right? So you can substitute and you will be getting A1 is minus 4. What does it mean by minus 4? If this 3 degrees thing is kept like this, then this 4 degrees thing has to be kept in the opposite orientation. That's the meaning of minus 4. Then deviation happening because of this guy, and this guy will be getting cancelled. Now if a ray is going like this, it will be deviating opposite to this thing, right? If you have seen the figure, if a ray is going like this or like this, it will be deviating away from this angle, away from the angle of the prism. So it will be deviating away from the angle of the prism. Now again it will be passing through this, it will be deviating away from the angle of the prism. This deviation and this deviation will be getting cancelled. A point object is placed at origin, the refractive index of thin prism, angle is 2 degrees, right? So again we will be seeing what is mu minus 1 into A. So what is the deviation? Mu minus 1 into A, which is 1 degree, that is pi by 180 radian, pi by 180 radian. So basically we can take 2-3 rays, or all the rays which are going like this, all the rays will be rotated by angle 1 degree. So basically all the rays which are emerging from here, they will be rotating by 1 degree. So you will be feeling the image is somewhere here. So the people who are here, they will observe those rays will be coming from somewhere here, where all the rays are rotated by 1 degree. Now this ray I have drawn for my reference. Generally we don't draw it like this inside, because we know like refraction will be happening here and here. This is for the reference. So if there is some ray going like this, probably you can draw only till here. So that will be deviated by 1 degree. So you will be assuming the people who are here, they will be feeling that it is coming from here. Now what is this angle? This angle is 1 degree and this length is 5 centimeter. 5 centimeter. So what is this length? This length is r theta, right? Theta is small, so you can go with that length is arc length, r theta. R is 5 and theta is 1 degree. So that is going to be, it is not 5 pi by 36, it is pi by 36. It is pi by 36, it is not 5 pi by 36, it is pi by 36. 5 theta, 5 theta. It is pi by 36. So from there you will be getting option A and B correct. The coordinates of image formed due to first refraction is 0, pi by 36. This is pi by 36. First option is correct. O behaves as an object at a distance 25 centimeter on the left of the mirror. So this is 20 plus 5, 25. Yes. Option B is also correct. The x coordinate of image formed by concave mirror. Okay, so now this will act as object for this mirror. Now, if the object was here, then okay, anyway, incident rays are going this way, so that is positive direction, this is negative direction. So object distance is minus 25, focal length is minus 30. So when you substitute, you will be getting V is 150. The meaning is image will be forming on this side, which is virtual image, and at a distance 150 from the pole. 150 from the pole. Magnification is minus V by U. You will be getting it as 6. The meaning is if the object size, image size will be 6 times. So if the object is here, image will be formed at 150. So that's what we understood. But object is not here, object is here, whose length is pi by 36. Object is here. So basically you can visualize some imaginary arrow. If the object is here, image would have formed here. If the object is imaginary arrow, then the image will be imaginary arrow and with the same orientation. Right, magnification is positive. And how much times? It will be 6 times of this. 6 times of this. This length will be 6 times of this. So it will be at a distance 150 and 6 times of that is pi by 36. So y coordinate is going to be pi by 36. Sorry, pi by 6. 6 times of pi by 36. So y coordinate is going to be pi by 6 and x coordinate. This is 150 and this is 25. So totally 175. So x coordinate is going to be 175 and y coordinate is going to be pi by 6, right? So this is pi by 36, okay? Yeah, okay, so probably you can try this question by yourself. This involves small angled prism, angle of deviation is mu minus 1 into A, and it involves if the mirror rotates by angle theta, reflected ray will rotate by 2 theta, right? And in the next class, we will be seeing refraction at the curved surface. So reflection at the plane surface, reflection at the curved surface, refraction at the plane surface and refraction at the curved surface. This is the sequence, right?